All right, we are recording. So, hello everyone, welcome back to the SPS seminars. Very nice to seeing you all. Thank you very much for joining us today. So today it's my great pleasure to introduce you to another amazing speaker that we have in this series, Céline Gicquel. She's from Université Paris-Saclay in France, and she's an associate professor in operations research there. She obtained her PhD in industrial engineering from the École Centrale Paris in 2008. And also I got this HDR, I suppose, the accreditation to supervise research from the university in 2021. And her research interests involve modeling and solving highly combinatorial optimization problems, especially those coming from applications in various fields like manufacturing, energy, and transportation. And she also worked, among many others, on the development of stochastic integer programming approaches, especially for lot sizing and facility location problems. So today she will also tell us a little bit about the slot sizing problem, but especially SDDiP algorithm that we are very curious to hear about. Thank you so very much, Céline, for joining us, and the floor is yours.
Thank you, Marie, for the nice introduction. And also thank you for inviting me and giving me the opportunity to present this work. First, I would like to highlight the fact that this is a joint work with Franco Quezada, and former PhD student of mine, and Safia Kedat Sidoum, a professor in Paris. So what will be in this talk? Basically, we're going to focus on a combinatorial optimization problem arising in manufacturing. So this problem is called lot sizing. And here I'm going to investigate a stochastic variant of this problem that we're going to handle via multi-stage stochastic integer programming. So in order, our focus will be on an attempt at solving large size instances of the problem. So first, we will discuss the direct application of the stochastic dual dynamic integer programming, the SDDiP algorithm for this problem. And the main contribution of the work is an extension of this algorithm, mainly aiming at improving its numerical efficiency to solve large size instances. Okay, so the outline of my presentation will be as follows. I will first give you a brief introduction on deterministic lot sizing, tell you what this problem is about, and also give you some flavor about the polyhedral knowledge that we have, the polyhedral structure of this problem. Then I will move on to the stochastic extension, which will be the main subject of this talk, the stochastic lot sizing. I will then explain how we can solve it when directly applying the SDDiP algorithm as it was published a few years ago. And then I will try to explain when we encountered many numerical difficulties when trying to use this algorithm directly. So I will try to explain what was the causes of this difficulty and how we tried to go around and propose this new extended variant, which we call the extended SDDiP algorithm, which has as a main objective to be more efficient at solving lot sizing problems. I will then give you a very brief overview of our numerical results and finish with a conclusion and some research perspective. So basically what we're talking about here is combinatorial problem, combinatorial optimization problem coming from industrial production. So very basically, production is a process of converting raw materials or semi-finished goods into finished products, so as to satisfy a customer's demand. So behind this very generic definition, we have a huge variety of industrial realities. This can be, for instance, float glass production lines, car assembly lines, some lines cooking things, or luxury products production. So behind this is industrial production. And one thing that I'm going to discuss a lot in this talk is inventory. So again, basically, inventory is a set of all goods that a company holds to be used in the future, either to be sold directly to the customers or to be used in production, in further production. And again, behind the term inventory, we have a very wide variety of situations. We can have bulk products stored in tanks, powder products stored in big bags, pallets stored in racks, or even finished cars stored on a car park. So the topic of my talk will be production inventory system. So on the basic variant of this production inventory system, involving a single production resource. So here you can imagine a machine in a factory, an assembly line, an oven cooking something. And this single production resource has an unlimited production capacity. It produces direct finished products directly from raw materials using a single production each-line, and we are considering a single type of product. So a very basic situation in terms of production inventory system. And our focus will be on planning production on this system, which means we are going to look into the future and decide when and how much we're going to produce on the resource, when and how much to store in inventory, and this to satisfy customer demand on time and minimize the production cost for the company, while of course taking into account all the technical limitations of the system. So this is a general definition of production planning, and lot sizing is a specific case of production planning in which we have the following characteristic, the following features. First, in terms of the demand, we are looking into the future and considering a finite horizon decomposed into a discrete set of planning periods. And so, for instance, you can imagine a planning region of 2 months divided into 8 one-week periods, or a 2 weeks origin divided into 14 days. This depends on the industry. And the idea is that at the end of each period, we have a time-varying demand denoted by DT to be satisfied on time. That is, we cannot be late and we cannot backlog the demand. We have to satisfy it on time, at least in this basic time. In terms of production costs, dynamic lot sizing, they are characterized by 2 main sources of cost. The first one are fixed setup costs. These are costs that we need to pay each time we have to produce something on the resource, and this whatever the produced quantity. So for instance, these fixed setup costs, they account for the preparation time on the resource to install the right tool on the resource, for instance, or to clean a chemical reactor in between 2 batches, or to heat up an oven up to the right temperature. And the main idea is that this costs, the amount that we have to pay for it, does not depend on the quantity that we're going to produce after. So these are fixed setup costs. And then we have linear inventory holding costs. So these are the costs that we have to pay each time we want to keep a product in inventory from one period to the next. So each time we want to anticipate demand satisfaction, 1 or several periods in advance, we have to pay for it. And the amount is proportional to the amount of products stored and for the duration of this storage. And the whole point of lot sizing in general is to find a production plan over this discrete planning horizon, which is feasible in terms of demand satisfaction and technical limitations of the system, and which provides the best possible trade-off between these fixed setup costs and this inventory holding costs. And the difficulty here is that these 2 costs, when taken individually, they lead us to make totally different production planning decisions. So to find this best trade-off is not so easy in practice. Just let's have a look at a small illustrative example to highlight this trade-off that we are seeking to find in lot sizing. So let's consider a very simple instance with a planning horizon of 4 days. And at the end of each day, we have to satisfy this demand. You see that this time-varying demand. We assume that we have no initial inventory. And each time we want to produce something on the resource, we have to pay 15 euros. So these are the setup costs. And each time we want to anticipate the demand, then we have to pay 1 euro per unit held in stock per period. Okay, let's have a look at the first simple strategy. If we just look at if we just look to minimize the setup costs, then we will we will decide to produce all the demand, that is all these 25 units here, in the first period, using 1 single lot of very large size. So we will carry out only 1 setup on the machine, so we will pay only once the setup cost. But we will have a lot of anticipation. We're going to produce all the products quite in advance, and so we will have a high level of inventory holding costs. So here, using this simple strategy, we will have a total cost of 56 euros. If we go for the opposite strategy, where we decide to produce each product as late as possible. We're going to produce in each period the demand for this period. So we call it sometimes a lot for lot strategy. In this case, we will have no inventory holding cost, but we will have to carry out 4 setups, so this will be more expensive. And finally, of course, the idea of lot sizing is to find the best possible trade-off between these two opposite strategies. So here, in this very simple case, we have 2 products in one in period 1, one in period 13, and for a total cost of 45 euros. Okay, so that was just a brief introduction to lot sizing. So now let's have a look at more mathematical modeling. This problem, it can be modeled as a mixed integral linear program. So in a deterministic setting, we would introduce 3 sets of variables. First, continuous variables to decide about the production quantity in each period t, xt, and continuous variables to decide about the inventory level at the end of each period. And then we will have yt variables, so set of variables, binary ones, to decide whether or not we produce something on the resource and to pay the corresponding setup cost. This gives us the following MILP formulation. We want to minimize the sum over the total with the horizon of the setup and inventory holding cost. Then we have a set of constraints to link production and setup variables. So as long as I want to produce something, so as long as xt should be non-negative, then yt will have to be set to 1, and we will have to pay the setup cost. Then we have inventory balance equations. So these are to ensure that at the inventory level at the end of period t is equal to what we have at the beginning of the period plus what we have produced minus what has been retrieved from inventory to satisfy the demand. So this problem, it has been around for quite a long time. The first formulation dates back from the 50s. And we know that it is polynomially solvable. We have an efficient dynamic programming algorithm to solve it in its deterministic setting. But what we will be interested in the sequel of this work is to solve it as a mixed integral linear program directly with mathematical programming solver. And here we are faced with one difficulty, which comes from the presence of a large number of big up type constraints, these constraints here, which usually have a very negative impact on the LP relaxation of the problem. So for lot sizing problems, it's quite common to have integrity gap like 40, 50%. If you don't do anything, you can really have a poor LP relaxation. So the difficulty at solving this problem formulated as such can be quite significant. So luckily, we have some polyhedral knowledge about this problem. In particular, we have on hand a set of very strong valid inequalities. You don't need to understand all this formulation here, but just keep in mind that these valid inequalities are very strong. They provide a complete description of the convex cell of the feasible space of this whole problem. They are polynomially separable. And so they are very efficient in a deterministic setting. The one thing that I would like to highlight is that in order to use these valid inequalities, we need to have this cumulative demand, DCL, which represents the demand of a set of periods, a set of subsequent periods. Which means that if we want to use these valid inequalities, we need to have some visibility of the demands that will need to be satisfied some periods ahead of time. So please just keep this in mind, because this will be one of the difficulties that I'm going to mention later. Okay, that's it for the deterministic introduction on deterministic lot sizing. I will now try to move on the stochastic expansion. So we are investigating here a stochastic expansion in which all the input parameters, demand and cost, are subject to uncertainty. We assume, as common in stochastic programming, that we have a known probability distribution for these random parameters. And here we consider a multi-stage sequential decision-making process. So here, what we consider is that we are at the beginning of stage 1. So first thing, here in this work, to make things simple, I'm going to equate a decision stage with a production planning period. In practice, this may be subject to some discussions, but here, to make it simple, let's assume that a stage is equal to a period t in terms of production planning. So let's assume we're at the beginning of stage 1, of period 1. We know that we have a 0 initial inventory, and we observe the realization of the demand and set the cost, and then we make our planning decision for stage 1. We decide whether or not we're going to produce, how much we're going to produce, give us our decision for stage 1, and then we will have a living inventory at the end of period 1, and using this data plus the newly available observed value of the demand for stage 2, we will make our planning decision for stage 2, and so far and so on till the end of the horizon. So this clearly leads us to a multi-stage stochastic programming approach. And in order to obtain something which is numerically tractable, we're going to use, as common in this field, a scenario tree. So here I have again my 4 planning periods here, 1, 2, 3, 4. And now I will represent the unfolding of the uncertain parameters via a scenario tree. So each node head corresponds to a realization of the stochastic parameters up to the corresponding period. We have for each node a single predecessor in the tree and a set of children, the n, and each node has a given probability of occurrence, and it corresponds to a given value of the setup, inventory holding cost, and demand. So given this modeling of the uncertainty, we can come up with a formulation of our stochastic problem as an MILP, using the same decision variables as before, but indexing them by the node rather than by the period. So we'll have production, inventory level at node N, and setup at node N. This gives us the following MILP formulation, where we seek to minimize, so it really looks the same as the deterministic one, in fact, but we now seek to minimize expected setup and inventory holding cost of the whole scenario tree. We have a set of the same set of constraints to link production and setup and the same inventory balance equations, but now the entering stock is the one leaving the ancestor node in the tree and not the one leaving period T minus. So what we have here is an MILP displaying the same structure as the one that we know for quite a long time in the deterministic setting. So a first idea, if we want to solve this MILP, is to try to use the same polyhedral approaches, the ones that we know work very well in a deterministic setting, to solve this MILP. So basically what we can do, the first idea is to look at each path here in the scenario tree, for instance, the path going from 1 to 4, to consider that this corresponds to a deterministic realization of the demand, and to then apply on each of these paths these valid inequalities that we know work very well in a deterministic setting. That's the first idea. The second idea was proposed quite some time ago by Guan and co-author, and they proposed to combine this, what they call path inequalities, that is deterministic valid inequalities expressed on each path on the scenario tree, to combine them together to obtain stronger inequalities expressed on subtrees. Okay, so this is the first way of solving this problem. What we found is in a numerical experiment that this polyhedral approach, like trying to solve this MILP as a whole, is efficient till, for instances, up to 1,000 scenarios more. But if we want to go further to solve the problem on larger scenarios, that is scenarios involving more stages or more children per stage, then we are faced with major numerical difficulties. So this is why we tried to implement a recently introduced algorithm in the literature, which is the SDDiP. So for those who know it, the SDDiP algorithm is a direct extension of the SDDiP algorithm, which is well known for multi-stage linear programming, to the case where we have integer variables or binary variables in the problem. So let's have a look at the SDDiP. It really works the same as the SDDiP. The main difference is in terms of which cuts are generated in the backward step. So basically, this SDDiP algorithm, it can be seen as a full decomposition approach. in which we're going to decompose the problems expressed on the whole scenario tree as into a large number of very small subproblems, each one being expressed on single node subproblems. So if you have a closer look at these single node subproblems, it look like this. For instance, let's assume we consider the subproblem as expressed at node 3. It has as input data the entering stock that is the S1, the stock leaving its parent node. It knows the actual value, the current value of the setup cost, inventory holding cost, and demand, and it will make planning decision for this given node, the node 3. So it will decide about X3 and Y3. Of course, if we just looking at its current cost here. Of course, if we do this, we are totally myopic. We totally forget the impact of our planning decisions on the future. So in these subproblems, we introduce expected cost to go function, representing an assessment of the future cost as a function of the living stock Sn. Okay, these are the single node subproblems. For the SDDiP, we introduce one meta assumption, which is the stage-wise independence, which basically needs that there are no time correlations in the stochastic process. And this allows us to make one meta simplification that is instead of having one of these expected cost to go function for each node, we have one of these for each stage t, qt. So we drastically reduce the number of expected cost to go function that we will have to handle in the algorithm. And what the SDDiP does is it builds a piecewise linear under approximation of this qt function iteratively. So at some point, the actual subproblems that we will have to solve looks like this. We have theta n, which represents the value of qtsn, and theta n is the value of theta n is driven by a set of linear cuts. Here I have the set of cuts which have been generated from period 1 from iteration 1 to a I of the algorithm. So what we do with each of these SDDiP algorithm, it's the same as in SDDiP algorithm. In fact, we first have a sampling step in which we randomly choose a path in the scenario tree, then a forward step in which we solve each of these planning problems, single node planning problem. So here I first solve a small problem at node 1. So give me a living inventory S1, which I use as input data to plan production at node 3. Once this is done, I obtain a living inventory S3 and so far and so on till I reach the living. And then all this, we do it using our current approximation of the expected cost to go function, Q1, Q2, and Q3. And then in the backward step, we go in the other way around from the leaf nodes towards the root nodes. So what we do is we solve some relaxation of the subproblems expressed here, and we use information provided by this relaxation to generate a cut here, and a new linear cut, which is used to improve our approximation of Q3. Then we do the same here for these three subproblems to build a new cut to add to Q2, and so far and so. Okay, the main idea of the SDDiP algorithm as compared to the SDDiP algorithm is which cuts do we generate here in this backward step. In the paper by Zhu and Kosos, they propose to use 3 different families of cuts: integer optimality cuts, Lagrangian cuts, and stressing bundles cuts. So now let's have a look at what this gives as a result of node sizing. First, this SDDiP algorithm, it has some major advantages because it transforms. We go from the resolution of a huge MILP formulated on the whole scenario tree into the resolution of a large number of very small MILPs. If you have a look at the problem as it is formulated here, so let me go back here. So we have basically one single set of variables, yn, and 2 continuous variables. So it's really a tiny problem in terms of number of variables, much smaller than the first one. And also, if we apply the algorithm as recommended in the paper, we have, theoretically speaking, finite and optimal convergence, which is guaranteed. But in practice, we were faced with many difficulties when trying to apply this algorithm directly on lot sizing problems. So we tried to understand why, and I will try to give you the cons of this algorithm. The first thing is that in the SDDiP algorithms, we have quite a number of expected cost to go functions to approximate. In fact, t-1 here, for instance, have to approximate Q1, Q2, and Q3. And also, this means that in the first iterations, the production planning decisions that we make are of very poor quality. For instance, here, let me go back to the forward state. In the first iterations, when I'm solving the problem at at node 1, I have no clue about the impact of my planning decision on the future, so I make very myopic decision. Basically, what's happening is that at node 1, we produce a demand for D1 for node 1 and do not anticipate at all the future demand. The same at node 3, node 8, and node 23rd, meaning that, in fact, we are producing using what we call a lot for lot strategy, one of these extreme strategies I was discussing in the deterministic setting, where in each period we produce a demand for the given period without looking at all ahead into the future and trying to anticipate the future demand. So usually this means that we are paying a huge amount of setup costs, which is much higher than what the optimal strategy would do. So that's the first source of difficulties of the SDDiP. The full decomposition means that we are making very myopic decisions at the beginning because we cannot at all anticipate the future demand. The second difficulty comes from the fact that in order to get this theoretical convergence of the algorithm, state variables should be binary. But in our case, the state variable are inventory level variables that are continuous. So we need to carry out a binary extension and to replace Sn by a set of binary variables UBM in order to apply the SDDiP algorithm as it was published. So this means that we are introducing additional variables in the formulation of each subproblem. Then the third difficulty comes from the need to generate Lagrangian cuts in the backward step. So if you remember well, I didn't go into every technical detail here, but among the cuts that need to be generated in the backward step, we have Lagrangian cuts. And these ones are very costly in terms of computation time to generate, because we need to solve a Lagrangian dual problem by a subgradient algorithm to get the value of the coefficient mu and nu here. So they are needed to have this guarantee of convergence, but numerically speaking, they are difficult to handle. And finally, the fact that we have totally decomposed the problem means that each subproblem only see the demand, the current demand, has no clue about the future demand, and all the previous knowledge that we have on lot sizing, especially all this family of valid inequalities that we know are very efficient in a deterministic setting, we cannot use them simply because we don't have the information on the future demand when we are considering single node subproblems. Okay, so this means that what we observed in practice that this SDDiP algorithm, it has a rather slow convergence on lot sizing problems. So what we propose is an extension of this algorithm trying to tackle these difficulties. And this extension, it comprises 3 main ingredients. So I'm going to introduce them one by one. First ingredient is to replace the full decomposition by a partial decomposition. So the idea is that rather than decomposing the problem expressed on the whole scenario trees into a very large number of very small single node subproblems, we're going to use a partial decomposition of the problem into subproblems defined on subtrees. For instance, here I'm going to consider a problem expressed on this subtree, a problem expressed on this subtree here, and so on. So in terms of the subproblems that need to be solved, then we look exactly the same as before. So we have an entering inventory at the root node here. then we make our planning decision considering this time all the nodes of the subtree W eta, and then we have leaving inventory at each leaf nodes here of the subtree, which are then, and we use the expected cost to go function of the corresponding stage to evaluate the impact of our planning decision on this subtree on the first. Okay, so the extended SDDiP algorithm will do the same as the SDDiP. So we will build piecewise linear under approximation of this QT by a set of linear constants that we will generate iteratively. So what if we look at what we do during one iteration? So we have again a sampling step where we randomly choose the path. Then we solve first a small subproblem expressed on this subtree here. We record the leaving inventory at node 3 and use this as the input data to solve a small stochastic problem expressed on this subtree here. And then on the other way around, in the backward path, we solve a relaxation of 3 small, let's say, stochastic problems here, and use the information provided by this relaxation to generate a cut that will be used to improve our approximation of Q2. And the good point is that this cut can also be used to approximate, can also be used to assess the future cost at leaf node 2 and 4. Yeah. Okay, so what do we hope with this partial approximation rather than full approximation is that the production planning decision we make will tend to be less myopic. For instance, in the forward step, the decisions that will be made, for instance, at node 1 here, at least they will have a visibility on the demand to be satisfied in the next period at node 2. And we have some chance that to avoid this costly lot-for-lot strategy, and that some part of the demand that will have to be satisfied here will be anticipated at node 1 if it is cost efficient, I would say. And as we have also less expected cost to go function to approximate, what we expect is that the quality of the solution will tend to improve quicker, and so we'll have overall less iterations to do than in the full decomposition approach. Of course, each of the subproblems that we need to solve here, it is larger in the partial decomposition approach than in the full decomposition, because we are now solving problems expressed on subtrees rather than on single nodes. But again, we can use these valid inequalities that we have on hand to try to improve and reduce the computation time to solve each of these subproblems. So this is the first ingredient, partial decomposition versus full decomposition. Second ingredient, it was also discussed, I think, in a previous paper on unit commitment, if I remember well, is to use an approximate version of the SDDiP algorithm before actually running the exact algorithm. In this approximate version, we will keep our continuous state variable Sm, so we will avoid the introduction of binary variable in this binary expansion. And we will generate only one type of cuts, the one which are called the stress unbalanced cuts in the backward step. And these cuts, they are much easier to generate than Lagrangian cuts. Of course, by doing this, we are losing the theoretical guarantees that our algorithm will converge towards an optimal solution in a finite number of steps. But at least in practice, we hope to obtain a good approximation of the expected cost to go function with a reduced computational effort. So thus keeping our effort for the second phase, and then when we see that there is no improvement anymore that can be obtained from phase 1, then we go to phase 2, and phase 2 is the regular SDDiP algorithm with binary state variables and the generation of all types of cuts. And then we regain the theoretical guarantee that the algorithm will converge. So this is a second ingredient, like a two-phase algorithm with a phase 1 which runs an approximate version of the algorithm, which is not theoretically speaking as beautiful as the original proper algorithm, but which is more efficient, at least in the first iterations, to quickly approximate the expected cost to go function with a reduced effort. And the last ingredient is the use of valid inequalities. So I've already mentioned during phase 1. So I've already mentioned them as a way to, of course, speed up the resolution of each of these sub-problems. But here I would like to discuss another way of using them. To understand it, we need to focus on what we do in phase 1, where we generate these stress-embedded cuts. So basically, these cuts, they are like Bender's cuts with a slight modification for nu. But here, basically, to obtain the value of the mu and the nu involved in this cut, we need to solve for each relaxed subproblem. This relaxed subproblem. So let's consider maybe that we are here. So here I'm trying to discuss the relaxed subproblems that they need to be solved here, in and here, to generate these cuts here. So this subproblem, in case of the stress-embedded cuts, it looks like this. It's a linear program in which we have relaxed the integrity constraints of yn. We have introduced some copy constraints on the entering inventory, and we consider the dual value of these copy constraints and use the dual value of these copy constraints to find the value of the coefficient mu here. We can do this for linear relaxation, the initial one, the one which is formulated here, but we can also do it for other relaxation, that is relaxation stressing by path valid inequalities and by tree valid inequalities. And the good point is that depending on which linear relaxation we use to generate the coefficients, we will find different dual values for the copy constraints here, and this will give us different values for the mu and the nu. So we can basically leverage the existence of alternative LP relaxation of pelotizing problem to generate a wider set of stress-embedded cuts during phase 1. And so we will again try to build good approximation of the expected cost to go function using easy to generate cuts rather than Lagrangian cuts. So now let's have a look at the numerical results. So here we just give you a very basic description of these results. So we considered a set of 140 randomly generated instances involving between 4 to 12 stages, which means between 1,000 up to 3.2 million scenarios. All the LPs and MILPs that needed to be solved within this SDDiP or extended SDDiP algorithm, they were solved using simplex form. So let's have a look at the results. So I'm using as a performance criterion the optimality gap after half an hour of computation. So over the full set of instances, if we use the polyhedral approach, that is, if we seek to solve the extensive MILP formulation, considering the whole scenario tree in one go, we obtain quite a huge optimality gap of on average 40% over all the instances. Now, if we directly apply the SDDiP algorithm, we obtain quite a good reduction, but we are still around 20% of optimality gap, meaning that a direct application of the SDDiP is not so efficient. It's better than tackling the problem using a polyhedral approach, but still there are room for improvement, I would say. Then if we had the first ingredient, that is the partial decomposition instead of the full decomposition, we can reduce this optimality gap on average up to 11%. And these results are obtained without using any valid inequalities, not even to speed up the resolution of the subproblem. That is just allowing the production planning decisions to be made, having a better visibility of the demand to be satisfied, and reducing the number of expected cost to go function. In this case, it gave us quite a nice improvement. Then if we had the second ingredient, which is this approximate phase, or this first phase, where we run an approximate variant of the algorithm, we can obtain a second improvement and reduce the optimality gap up to 10%. And finally, if we add the third ingredient, the one where during phase 1, we try to exploit the fact that we have alternative LP relaxation of the subproblems to generate a wider set of stress-invariant scales, we can reduce the optimality gap up to 5% on average. Okay. Of course, if you want more details about the results, we can discuss it. Yeah, it was just to give you an idea about the kind of things that we could. Just to conclude, so here I have discussed solving a combinatorial optimization problem arising in manufacturing, and more precisely, stochastic and capacity load sizing, via multi-stage stochastic integral programming approach. And the main contribution of this work was the proposal of an extension of the SDDiP algorithm, mostly to make it more numerically efficient. This extension, it comprises 3 main ingredients: partial decomposition versus full decomposition, the addition of a new approximate phase before running the exact algorithm, and the generation of a wider set of stress-invariant scales based on alternative LP relaxation. And we see that by combining all together the 3 ingredients, we could obtain a significant improvement of the solution quality. So what are our perspectives? The first thing is that all this work was done on a very basic variant of load sizing problem, in fact, the simplest load sizing problem that we know. And of course, the actual production planning problems, they are much complex. So there is a need to seek to extend this work on more realistic load sizing problems. And also one thing that might be interesting is that this assumption, all this SDDiP algorithm, it relies on the assumption that we have stage-wise independence, so no time correlations. But in production planning, we know that there might be some negative correlations, especially regarding the demand, because if a customer tends to have ordered more than expected in a given period, it is likely that in the next period it will order less. And so there are some kind of cannibalization effect in between periods. So it would be nice if we could integrate these correlations into this solution approach. Okay, thank you very much for your attention. If you want to know more about this work, we have 2 paper versions. One exactly this work that I have discussed today, and one on a more realistic, at least somewhat more realistic problem dealing with manufacturing planning.